All right, so in this last section here, we're going to take a look at solving triangle problems, trigonometric problems. So we might be using some sine, cosine, tangent ratios, or we might be using the sine law and the cosine law, or a combination thereof to solve these problems. So if we start with looking at Tracy here and her tree problem, we got Tracy, who's 1.65 meters tall. She's standing 10 meters away from the base of a tree, and she measures the angle from the foot to the top of the tree. From her point of view, the angle is 50 degrees. How tall is the tree? So this may sound like something we've done before with similar triangles and things like that. However, here we have her measuring an angle from her point of view, which means from her head, specifically be from her eyes, but we're going to assume from the top of her head. She's measuring this angle. And that will allow us to get a slightly different diagram. So here we have our tree that we're looking for the height of. Over here will be Tracy. And so she is 10 meters away. And then she measures from the bottom to the top of the tree. So from her point of view here, she's measuring out 50 degrees, and she is 1.65 meters tall. So now we can use this information here to find the height of the tree. Now if we look at the tree's in this non-right triangle. We're probably going to need the sine of the cosine law in this case, but we don't have enough information. We have this pair here, but we have no other angles or sides in the triangle. However, if we use our right triangle that we have here with Tracy and the ground, then we can find the hypotenuse. We can also find this missing angle in here, and both of those will allow us to solve the larger triangle. So let's start with, we'll call this x, and we'll find side x. So side x squared equals 10 squared plus 1.65 squared. You are welcome to use the trig ratios here as well to solve this first for the angle and then solve for x. But we got the Pythagorean theorem that works just as well. So I have 10 squared plus 1.65 squared. So x squared is equal to 102.72 approximately, or x equals 10.14 meters. So there's our x value of 10.14 meters. And now theta in here, if we find angle theta, that's going to be a tan ratio opposite over hypotenuse, or sorry, opposite over adjacent. .165 divided by 10 is going to give me 0.165. And so tan theta, if I look that up in my table, is going to be about 9 or 10. Probably closer to 9. Yeah, let's say closer to 9. So theta is about 9 degrees. So there's my theta of 9 degrees. Now, how does that help us? Well, it gives us this angle in here. We'll call this angle alpha, because alpha is 90 degrees right here minus theta. So 90 minus 9. So angle alpha is 81 degrees. So I got that is 81 degrees right here. And now if I know those two angles, 81 and 50, call this angle beta. Beta equals 180 minus 81 minus 50. And so 180 minus 81 minus 50 will be 49 degrees. So we got this now as 49 degrees. We got that as 10.14. We got enough information to use the sine law. We got this pair and that pair. So the sine law is going to give us our side x, or we're looking for h, so let's start with h. H over sine 50 equals our x, which was 10.14, over 49 was the angle, so sine 49. And then we do a little bit of converting signs to decimals, and then cross multiply. Sine of 50 is going to give me 0.7660. Sine of 49 is going to give me 0.7547. So I'll cross multiply and divide here. 10.14 divided by 0.7547. It's going to give me 13.45 times 0.7660. And then when I multiply that, I'm going to get 10.29 meters. So our tree is approximately 10.29 meters tall. So it's a bit of work, but again, we use Pythagorean's theorem to find the hypotenuse of this triangle. We use the tan ratio to find the angle in here, which allowed us to find this angle because it was 90 less than 9, which that worked out to. Once we knew these two angles, we could find that angle. Having that angle and its opposite side, having that angle, we could find its opposite side using the sine law. So we're just combining some of our trigonometric identities and functions to solve these. One more here. We have a baseball diamond is a square with 30-meter sides. It's a diamond, sir. Yes, a diamond is a square that is rotated specifically, but it's just a type. It's just another name for a square, essentially. And so our baseball diamond is a square with 30-meter sides. The pitcher's mound is 30 meters from home plate on the diagonal between second and home plate. How far is first base from the pitcher's mound? So what we have is our baseball diamond and then here's home, here's second. So on this diagonal here, we will find the pitcher's mound 30 meters away from home plate. So we're not sure exactly where that 30 meters is. Probably somewhere up here. So we're going to call that the pitcher's mound. There is first. So we're looking for this distance here. So this isn't going to make us a right triangle. We got 30, we got 30, and we got x. So we don't know how far that is. We don't have any angles listed here, but this here angle, because it's a square, this total angle is 90. And if we cut that in half to go from home to second, this is going to be 45. So that's 45 degrees. There we have an angle in between two sides. And we can use the cosine law. So this is simply a cosine law. X squared equals 30 squared plus 30 squared minus 2 times 30 times 30 times the cosine of 45 degrees. So that's all it is there. And again, you could do this step by step, or you can do this all in your calculator. In either case, you should get the same answer. I'll do it step by step for us here. So 30 squared is going to give us 900 plus 900 plus 900 minus 2 times 900 is going to be 1800 times the cosine of 45, which is 0.7071. Multiply, and then we'll do our addition and subtraction. 900 plus 900 minus 1800 times 0.7071 is 1272.78. And so when we do our subtraction, x squared equals 527.22, or x equals the square root of that, which is 22.96 meters. So the pitcher's mound is 22.96 meters from first. All right, so a little bit of thinking here on setting up our different triangles to solve, but once you get them set up, find the various parts along the way. Again, sometimes using a mixture of right angle triangle trigonometry and non-right triangle trigonometry to solve those.